So let's talk about systems of measurement. Measurements depend on units that serve as reference standards. And the standards of measurement that are used in science are those of the metric system. What we have in this picture here on the left is the kilogram, and what we have on the right is the meter. Now, it's not a kilogram, it's the kilogram. This is the original piece of metal that someone just made, and this is original metal bar that someone just cut to its length and said, this is now a kilogram and this is now a meter. And every meter and every kilogram in the world is compared to these standards. You can see the kilogram on the left is under a double vacuum. That's just to protect it, to make sure that no atoms fall off due to cosmic radiation or something like that. It'll always stay the same mass, and they only take it out to make copies. The metric system has now been revised, and it's named the International System of Units, or SI for short. And like the metric system, it has simplicity. It's based on 10 or multiples of 10. And it might be difficult for you to learn at first because you're new to it. But once you do, I think you'll really like it because it's based on units of 10, it's very easy to convert from one unit into the other, which is something that you have to do a lot in chemistry. There are 7 base units, but only 5 are commonly used in chemistry. We use the meter, kilogram, Kelvin, second, and mole. There are a couple of others that you may become more familiar with if you take physics. So our first unit of the SI system measures length, and it is called the meter, and we abbreviate it with a lowercase m. Next we have mass. The base unit for mass is the kilogram, even though we probably more commonly use the gram. The abbreviation for that is kg. Temperature, the unit that we use in the SI system is the Kelvin, although sometimes we use Celsius, and that is abbreviated with a capital K. Next we have time. We measure that in seconds, and that is abbreviated with a lowercase s. And last we have amount. Amount in chemistry is measured in a unit called the mole. You'll be hearing a lot about moles later on in this course, and that's abbreviated with MOL. You just drop one letter. It's not quite an abbreviation, but it is what it is. So a measurement is a quantitative observation that consists of 2 parts. The first part is the number, and the second part is the scale or the unit. Each one by itself is meaningless, but together it is a piece of data that we can actually use to make sense of something. For example, 20 grams. If I just said something weighed 20, you wouldn't know what I meant by that. But if I say 20 grams, you know exactly what I mean by that. We can compare that number to our knowledge of what a gram is, and then we have some sort of understanding. Or 6.63 times 10 to the negative 34 joule second. Sometimes our units are derived. Joule is a measurement of energy. Second is a measurement of time. A joule second is just energy multiplied by time. Like I said, sometimes non-SI units are used in chemistry. We commonly use the liter for volume, Celsius for temperature, calorie for energy. Some units that are very common in chemistry are also derived units, like I said. They're made by joining other units together. For example, speed. We measure speed in miles per hour. To calculate your speed, you need to know the distance that you traveled and divide it by the time it took for you to travel that distance, and that's your miles per hour. So the math gives us the units. Another one in chemistry is density. It's measured in grams per milliliter, which is just the mass of our sample divided by the volume of our sample. It gives us grams per milliliter. All right, so next we're going to look at some of the units in a little more detail. First we have length. In the SI system, the basic unit of length is the meter, like I said. Length is the distance between 2 objects measured with a ruler. And we can make use of prefixes to make the units larger or smaller to suit our needs. You can't measure everything with a meter. A meter is pretty big. It's probably the length of your arm. But if we were trying to measure the distance of an atom with a meter stick, that'd be a little silly. So we need to alter the unit by changing the prefix. So you have a list of these prefixes on table C, and these are all the ones that we use in chemistry. So the first one is kilo. It is the only prefix we use that makes the number bigger. Now there's more, but we don't use them in Regents chemistry. Kilo means thousand, and the exponent is 10 to the third. So if you take, let's say, the number 1 and multiply it by 10 to the third, you get 1,000. You make that number 1 bigger. Next we have deci, abbreviated with a lowercase d. That means tenth, and the exponent for that is 10 to the minus 1. Centi means hundredth. It's a hundredth time smaller than the base unit that you're dealing with. For example, if we were using meters for length, a centimeter is a hundredth of a meter. The exponent for that is 10 to the minus 2. Milli is abbreviated with the lowercase m, and it means thousandth, and the exponent is 10 to the negative 3. Next we have micro. Now we're getting really small. The meaning is millionth, and it means 10 to the minus 6. Next is nano for billionth, and that's 10 to the minus 9. And last is pico, which means trillionth. This is what table C actually looks like. It's a tad bit less user-friendly than that last chart. So the factor and the prefixes and the symbol is there, but the words aren't. So you need to memorize that kilo means thousand and milli means thousandth. This takes a little bit of practice, but we'll use these numbers enough in class that you'll make sense of them. Next, let's look at volume. Volume is the space occupied by any sample of matter. To calculate volume for a solid object, you multiply the length times the width times the height. So we're going to get a derived unit from the length. So the SI system is the cubic meter. If the SI system for length is meter, if you multiply meter times meter times meter, you get the cubic meter, or meter squared. A more everyday unit that is typically used in chemistry is the liter. And of course, we can also change the meaning with those prefixes in front, like milliliter. There are several devices that we use for measuring liquid volume. We could use a graduated cylinder, and you'll be seeing these in class and in lab. We can use a pipette for transferring small amounts of liquid. You can use a burette, which is typically used for acid-base titration, something we'll be dealing with later in this class, but it's pretty much a graduated cylinder turned upside down with a little valve on the bottom that will let liquid out. You can use a volumetric flask. These are typically used for measuring specific amounts of a sample and preparing solutions. And then we have the syringe. Most people don't think about this, but it's exactly designed to administer specific amounts of liquid. Volume may not be constant though. So volumes of a solid, liquid, or gas generally increase with temperature. This is much more prominent for gases. Also for liquid, it's not as prominent for liquids, but it's pretty significant. So if you look carefully on something like a graduated cylinder, you'll see a little symbol like this at the top that says like TC or TD, 20 degrees Celsius. That means that instrument is calibrated to deliver that exact volume that you've measured using the little lines and reading it carefully, but only if your sample is at 20 degrees Celsius, which is about room temperature. If you have temperatures very different than room temperature, especially hotter than room temperature, the volumes of your liquids could change, and that will throw off your volume. All right, our next unit is mass. Mass is the measure of the quantity of matter present in a sample. Not to be confused with weight, which is a force that measures the pull of gravity. And weight can change with location, but mass can't. When working with mass, the SI unit for mass is the kilogram, but a more convenient unit for us is the gram. Kilograms are pretty big, and we won't be dealing with kilograms of samples of matter. We'll be dealing with much smaller samples like grams and milligrams. The measuring instrument that we will be using is a digital scale. It looks like this, and I'll teach you how to use it in lab, and it reads out to 1 decimal place. Much more accurate than the triple beam balances you may have used in middle school. Our next unit is temperature. We measure using the Celsius scale, which can be defined by 2 readily determined temperatures. The freezing point of pure water, which is 0 degrees Celsius, and the boiling point of pure water, which is 100 degrees Celsius. The SI unit, however, for temperature is the Kelvin scale, and it's determined only by one temperature, which is absolute zero, which is 0 degrees or 0 Kelvin. The reason we like the Kelvin scale in chemistry is that it doesn't give us negative numbers. You can get something colder than the freezing point of water, and that makes your math a little more complicated dealing with negative numbers. Using Kelvin and the absolute zero as a bottom number that can never be anything lower than that gives us no negative numbers, which makes the math nice. So sometimes we need to convert from one temperature scale to another. If you have a word problem and they give you the temperature in Celsius, sometimes you have to convert to Kelvin or vice versa. So the formula for this can be found on table T. Like all formulas in this class, you need to memorize very few formulas. You just need to know to go to table T to find it. And this is what the formula says. The Kelvin temperature equals the Celsius temperature plus 273. So let's do a practice problem. Normal human body temperature is 37 degrees Celsius. What is the temperature in Kelvin? So to do this, all we need to do is plug our values into our formula. So Kelvin equals 37 plus 273, which will bring us up to 310 Kelvin. Here's the other type of question they can ask. If Mr. W's classroom is 300 Kelvin, what is the temperature in Celsius? Okay, so now they give us Kelvin and want us to solve for Celsius. So all we need to do is plug in 300 Kelvin on the left and equals Celsius plus 273 on the right. Subtract 273 from both sides. That'll cancel out. And Celsius degrees will equal 27. All right, our next unit is energy. Energy is the capacity to do work or to produce heat. Energy can also be measured, and there are two common units that are used for energy. The SI unit is the joule, and it's named after James Prescott Joule. That's why I could say capital J, joule. And then we also have the calorie, and that's the heat needed to raise 1 gram of water by 1 degree Celsius. So picture a really tiny pot of water that can only hold a gram of water, which is about a milliliter. If you could measure the amount of heat that you would need to use to turn that water from, say, 20 degrees Celsius to 21 degrees Celsius, that amount of heat is 1 calorie. And then we can compare all other energy values to that number, and that's how we get calories. 1 calorie is equal to 4.18 joules, and sometimes you'll need to convert from one to the other. This number is not on your reference table though, so if I ever ask you to do this type of conversion, I'll give you the conversion factor, and we'll talk more about conversion factors in the next video. So let's sum things up here. So SI measurement units allow scientists to report data that can be reproduced by other scientists. We all use the same scale all across the world, so there's no confusion in the reporting of data or the drawing of conclusions. If you add prefixes to SI units, you can change the range of possible measurements from really big, like kilo, 1,000 times bigger than your unit, or really, really small, like pico, trillion times smaller than your base unit. You need to be familiar with the SI and metric units that are commonly used in chemistry, and also be aware that sometimes the measurements have derived units that come from joining other units together. So sometimes in our mathematical calculations, you'll get what the unit's supposed to be if you do the units correctly in the math work. And more on that in the next video. If you have any questions about this, please let me know, and I hope that makes sense.